All right, let's dive right into one of the deepest, most wonderfully strange ideas in all of physics, quantum entanglement. It's a concept that really makes you question everything you thought you knew about how the world works. So, let's get into it.
For over 100 years, quantum mechanics has been the absolute foundation of modern physics. We've tested its predictions with insane precision, and every single time it's been spot on. So as this quote here says, we have every reason to trust the math. What the quantum formulas predict, we expect to see happen in the real world. And that is where our story really begins. Because quantum theory doesn't just predict things that are a little bit odd. Oh no. It predicts things that seem to fly in the face of common sense, to break the very rules of reality as we experience it every day. It forces us to accept that the universe is just profoundly stranger than we could have imagined. So to really get this, we've got to rewind the clock a bit, back to a puzzle that seriously bothered one of the smartest people to ever live, Albert Einstein. Okay, so what in the world does that actually mean? Well, imagine you have two particles that are created at the same time, linked in a special quantum way. Entanglement means that they are now part of a single system. What you do to one particle instantly, and I mean instantly, affects the other one. It doesn't matter if they're a millimeter apart or on opposite sides of the galaxy. It's a fundamental connection that exists outside of our normal ideas of space.
And you know who just could not get on board with this idea? Einstein. He famously mocked it, calling it spooky action at a distance. For him, the idea that something could happen over here and have an instantaneous effect way over there, faster than light could travel, just had to be wrong. He and his colleagues were convinced that quantum mechanics wasn't the full picture. There had to be some hidden variables, some local rule they just hadn't discovered yet.
For decades, this was just a huge philosophical debate. You had Einstein's powerful intuition on one side and the bizarre, but so far successful, math of quantum theory on the other. But then, along came a physicist named John Bell, who figured out how to drag this argument out of the philosophy department and into the lab. He basically drew a line in the sand and challenged the universe to show its true colors. And what he came up with was, well, it was nothing short of brilliant. Bell created a mathematical test. You can think of it like a game with very specific rules. This test, called the CHSH inequality, was designed to figure out which rulebook the universe actually follows, Einstein's local common sense rules or the spooky non-local rules of quantum mechanics. Okay, so this slide just lays it all out, right? You've got two completely different ways of seeing the world. On one side, you have our everyday intuition, Team Einstein, if you will. The idea that things have their properties set in stone, and for one thing to affect another, something has to travel between them. And on the other side, you've got the wild quantum prediction. Properties aren't even real until you look, and these deep connections can exist without anything traveling between them at all. You can't both be right. So here's how Bell's test works. It sets a score. It says, look, if the universe is local and classical like Einstein believed, then when you measure the correlations between these entangled particles, the final score of the game can never go higher than a specific number. It's a mathematical speed limit for classical reality. And that number? It's 2. That's it. In any universe that plays by the local, common sense rules Einstein was holding out for, the score you get from this experiment absolutely cannot be higher than 2. That's the line in the sand. But what does the quantum rulebook predict? Well, quantum mechanics predicts a score of 2 times the square root of 2, which is about 2.828. And here is the absolute kicker. For the past 50 years, experiment after experiment has been run, and every single time, the results come in higher than 2. They come in right around 2.8, shattering the classical limit and matching the quantum prediction perfectly. So, what does that mean? It means the verdict is in, and the conclusion is just staggering. It's one of the most profound discoveries in all of science. Einstein, with all his incredible genius, was wrong on this one. The universe is non-local. The spooky action is real. Okay, so once the dust settled and everyone had to accept that this spooky thing was very real, the next question was pretty obvious. So, can we do anything with it? And this is where the story shifts from a deep philosophical question to the discovery of a powerful new tool. And this is just the perfect way to put it. What was once seen as a paradox, a problem with the theory that made people uncomfortable, is now understood to be one of its most powerful and useful features. Entanglement went from being a weird puzzle to a real, tangible resource, something we can actually harness to build technologies that were once pure science fiction. And we're not talking about small improvements here. These applications are potential game changers. Quantum cryptography could give us truly unhackable communication. Dense coding lets you pack more information into a single particle than you could classically. And then, of course, there's the one everyone's heard of, quantum teleportation. So let's quickly break this down, because it's wild. Now, this isn't Star Trek teleportation. We're moving information, not physical stuff. So first, you have Alice and Bob, and they each have one particle from an entangled pair. Alice takes a third particle, the one whose information she wants to send, and mashes it together with her particle. That measurement instantly changes Bob's particle way over where he is, but he doesn't know how it changed. So Alice has to send him two regular, classical bits of information over the phone, the internet, whatever. Once Bob gets those two bits, he knows exactly what operation to perform on his particle, and when he does, it transforms into a perfect clone of Alice's original. It's real, it's been done, and it works because of entanglement. Right. So just when you think you've finally got a grip on what entanglement is, nature throws us a curveball. It turns out, not all entanglement is the same.
It seems there are two basic flavors. First, you've got free entanglement. This is the good stuff, the high-grade, premium resource. It's called distillable because you can take a bunch of noisy, imperfectly entangled pairs and kind of purify them into a smaller number of perfect pairs that are ready to use for things like teleportation. But then there's bound entanglement. These pairs are definitely entangled. They're still spooky and connected, but you can't distill them. It doesn't matter if you have a million of them, you can't get a single perfect pair out. It's a much more mysterious, weaker kind of quantum link.
And you can just feel the surprise in this quote from the physicists who figured this out. The discovery of bound entanglement really threw a wrench in the works. It destroyed the simple, neat picture scientists were building and revealed that the structure of entanglement is far richer and, frankly, a whole lot weirder than anyone expected. So let's zoom out. After all this, the spooky riddles, the experiments, the mind-bending technologies, and the new mysteries, what's the big takeaway? What has this journey taught us about the nature of reality itself?
Well, first, it shows us that there is a deep, fundamental gap between the classical world we see and the quantum world that runs the whole show. They just operate by different rules. Second, and this is a really important point, even though reality is non-local, entanglement does not allow you to send a message faster than light. Remember the teleportation example? Alice still had to send Bob classical information. The spooky link is real, but it doesn't break causality. So quantum reality exists in this fascinating middle ground. It's definitely spookier than Einstein's universe, but it's not complete chaos either.
And that leaves us with this incredible, mind-expanding question. For the longest time, we just assumed the universe had to be local because, well, it just seems obvious, right? Entanglement showed us that our obvious assumptions can be completely wrong. And it just makes you wonder, what other fundamental, common-sense beliefs about our reality are just sitting there, waiting for the right question, the right experiment, to completely shatter them?